Welcome to Lab 3. In Lab 3, we are going to start out by having a given position set of a star orbiting a black hole of unknown mass. We're going to use this position set to find and approximate the mass of the black hole. To do this, we're going to use two principles. First one is Newton's second law. For Newton's second law, we know that the change in momentum is equal to F net times the change in time. And further derived, the change in momentum over the change in time is equal to F net. We get the change in momentum by taking the position and finding the slope between each one to get the velocity, then timesing it by the mass of the star. Also, we're using the law of gravitation. Since in this lab, we're neglecting all their forces and assuming that the only force in the system is the gravitational force from the black hole. We know that the gravitational constant is this. So from this equation, we get F net equals gravitational constant times the mass of the star times the mass of the black hole over the distance squared. We can derive this equation to get the mass of the black hole to equal F net times the position squared over the gravitation and the mass of the star. From this equation, all the other things we can find, we know F net is equal to delta P. We can find the distance between the star and the black hole since we know the position, and we have a gravitational constant and the mass of the star. Here is the initial conditions of all the given information. The first part of the code, we are going to find delta P over delta T. To do this, we take the velocity initial and the velocity final and times it by the star's mass to give us momentum. Then we take the final momentum minus the initial momentum to get the change in momentum. Then to further get dp dt, we take the change in momentum over the change in time. Then we're going to get net force. Since we know that dp dt equals F net, we therefore have that. The rest of the code is finding F net perpendicular and F net parallel, which I will discuss later. Then with our Python code, we find the distance squared between the star and the black hole. To do this, we take the star's position minus the black hole's position and square it. We then put this into our equation where we had F net equals G ms mb over distance squared, and which was further derived to the mass of the black holes equals F net times the distance squared over G ms. And this code can be seen right here. After being run, we see the motion of the star as it orbits around the black hole at the bottom. The yellow arrow pointing down is the net force acting on the object, which as you can see is pointed towards the black hole since that's the only force acting on the object, since we said that earlier. The blue line right here represents F net perpendicular, and the black line is F net parallel. To get these equations, since we know that dp dt equals dp dt parallel plus dp dt perpendicular, and that dp dt equals the final momentum minus the initial momentum over the change in time times the direction of p hat. Since we have parallel and we know that dp dt, we can thus find the perpendicular position. After the code was run, I got the F net perpendicular and the parallel force, and we can see that these forces add up to the final F net, which is true of this equation. Now a further discussion of F net and dp dt. F net is the net force. We know that the force acting on the object is responsible for the change of the momentum of the object. F net parallel is the force that's causing the object to either speed up or slow down, since this force is in the plane of r hat. And we know that F net perpendicular is the change of direction of the object. dp dt, which even though it equals F net, it is different because this is the observation of the object and its change in momentum over a specific time, but it does not cause any force on the object. Now for the what if question. What if there was a new black hole that was placed in the exact same location as the previous black hole that we found the mass for, and the position of the star orbiting remained the same? Would we be able to find a different mass for this black hole? I say that we would not. From this equation giving the force due to gravity, the mass of the star, the mass of the black hole over the distance squared, further derived giving us this equation, since the net force would remain the same, since the position vector remains the same, and dp dt would remain the same, this will not change. Since the black hole is placed in the same location as the last black hole, the distance between the two will stay the same also. And since g is a constant, and the mass of the star has not changed, the mass of the black hole must remain the same. That does it for Lab 3. Thank you for watching.